Okay, let's get started again. So in this part I want to talk about the Vatnik-Cerviniakis theory and look at how we can obtain classical results in terms of VC dimension using these Rademacher Averages ideas that we saw in the last hour. So the VC theory is really applicable when you're working in a minimax setting, when you worry about the worst case over probability distributions. The Rademacher averages, as we saw them, are a measure of complexity of a class of functions that's specific to a particular distribution. Okay, and it turns out that if you're worrying about maximal deviations between expectations and averages, they're the right quantity. All right? There's just this constant factor between the upper and lower bounds and some small number like 2 times square root 2. So they're the right quantity in that case, in the case of plus minus 1 functions when you're worrying about these maximal deviations between expectations and sample averages. The VC theory, working with the VC dimension, you can get an upper bound on Rademacher averages, and that upper bound applies for every probability distribution. Okay, so they're inevitably looser, right? They're concentrating on the worst case distribution. But we'll see that if you work in a minimax setting where you do worry about the best performance you can achieve for a given class of functions in the worst case over probability distributions, then the VC dimension is the right quantity there. Again, within a constant factor, although that constant is not so small. It's more like 20 or something. I guess we should see the specific formalization before we talk about constants. Anyway, so I want to start by telling you about the Vatnik-Cerviniakis dimension, how it's defined, and how it's related to something called the growth function. And then we'll look at what it implies about the Rademacher averages. Then in a minimax setting, we'll worry about, we'll see that this immediately implies that for the worst case over distributions, we can get some risk bounds, and we'll see a converse result that says that the worst case is really captured by the VC dimension. Okay, so let's start by defining the growth function. So again, we're working with the case of binary valued functions. We fix some class of functions, capital F, that map from our domain X to this set with 2 values, +1 and -1. And let's think now just about the case where we have some finite sequence of elements of X. Let's call them X1 through Xm. And so we're not talking about a sample here, we're just fixing M elements of X. And then we worry about the set of restrictions of functions in our class to this sequence X. So X is the M tuple, right? These M elements of X. If we look at the set of restrictions of F to X, these are vectors, right, with components f of x1 through f of xm. And the set of vectors, we take one vector for each element of our function class F. Okay, so these are vectors of length m. They take values plus or minus 1 in each component. So this is a subset of the m symmetric binary cube. The symmetric binary m cube. Okay, so these are restrictions of functions in F to this set. And the growth function we define as, we use this notation pi sub f for sequences of length m as the largest cardinality of this subset of the M cube. Right, so the maximum, this means cardinality of restrictions of f to x, maximizing over all sequences of length m. Okay, so this is how many different dichotomies of m elements of our domain can we get using functions in F. Okay, so it's another notion of the richness of a class of plus minus 1 valued functions. This function, I guess, that maps from length of sequences to the number of the maximal number of distinct sign sequences is another notion of complexity of our class F. Okay, so let's think of an example. Let's worry about linear threshold functions. I want to make it particularly trivial, so we'll look at linear threshold functions on the real line. Okay, so these are functions that map to plus or minus 1. They're plus 1 to some side of a threshold point, minus 1 to the other side. Okay, and we're allowing both directions. So let's suppose we're considering the case m equals 3. Right, our vector x is x1, x2, x3. Suppose these are all distinct, and I've chosen the indices so that they're in order. Right, x1 is less than x2 is less than x3. We have 3 points along this line. Then these are the sign patterns that we can get. Right, I've written out as rows of this table all the distinct 3 vectors in that set of restrictions of functions in f to x. Okay, we can get the all minus. Right, we can get the first point plus and the other 2 minus by a function that does this. I'm missing a picture here. That does this. Just goes down from plus 1 to minus 1 just between x1 and x2. And there's a function that goes down between x2 and x3. And we can get all 1s. We can do, and so on. Right, get minuses to the left of x3, and then x3 is a plus. So there are 1, 2, 3, 4, 5, 6 of these 3 vectors. And of course, the full set of all possible labellings we could get is of size 2 to the 3 is 8. So if this cardinality of restrictions of functions in our class to x, to a sequence x of length m, is equal to 2 to the m, then f is as powerful as it can be for that sequence of elements of x. It computes all possible dichotomies of x1 through xm. Okay, so when we're thinking about the growth function, in fact, in this case, this is you can't come up with another sequence x1, x2, x3 that gives a bigger table than this, that gives more rows than this, right? They're either distinct or they're not, and distinct you get more dichotomies. So the growth function is exhibited by any 3 distinct points, and it's equal to 6 at m equals 3 in this case. Okay, so just to remind you, the growth function for our class F for a particular value of m is the maximum cardinality of restrictions of f to that x. It's the number of rows in that table on the previous slide when we choose the sequence x that maximizes the number of rows in our table. Okay, so a couple of obvious things, that if we've got a finite class of functions f, then the growth function is no bigger than the cardinality of the class, right? We can't have restrictions, the number of restrictions exceeding the number of functions. And clearly, as m goes to infinity, right, the growth function must approach the cardinality of the class. Okay, if these really are distinct functions, then we have to be able to see that on these sequences if f is finite. And it's obviously always smaller than 2 to the m. I guess we saw that earlier. Right, 2 to the m is the total number of dichotomies of m points that we can achieve. So for linear threshold functions on R, the growth function at m is equal to 2m. Okay, why is that? Well, we arrange our m. Suppose we have m points. If they're not distinct, then we're not getting as many dichotomies as we could. So let's assume that they're distinct. That gives us the maximum number of dichotomies, and we can place we can get the all plus ones, the all minus ones, and then we can place our threshold points between all of these points. So that's 2 plus m minus 1 plus m minus 1 is 2m. Okay. More generally, for linear threshold functions on Rd, okay, which is doesn't have this nice order property. So here we're thinking about functions that map from x to I guess I've thrown away a threshold here, so it's a little different from this case. That maps from x to the sign of the inner product between x and a parameter vector w in Rd. The number of these dichotomies looks like, well, it's a binomial sum here, something like, and the terms here, the biggest order term is like m to the power d, right? It's m choose k, where k ranges, m minus 1 choose k, where k ranges from 0 to d. This is something that grows polynomially with m, and the exponent in that polynomial is d. Okay? So the VC dimension, the Vatnik-Cerviniakis dimension, is defined as follows. So if the cardinality of the restrictions of f to some sequence of length m is equal to 2 to the m, then we say that f shatters that sequence or that set, as I've written it here. Okay, so shatters means we get all possible dichotomies of the set. The VC dimension is the size of the largest set that's shattered by our class, and that's the largest value of m, equivalently the largest value of m for which the growth function is equal to 2 to the m. Okay, so we'll see that the VC dimension actually gives us very tight control of the growth function, that it's a single integer summary of the growth function. That up to the VC dimension, the growth function grows like 2 to the m. Right? Beyond the VC dimension, the growth function grows polynomially in m with exponent equal to the VC dimension. Okay? And there's no other kind of behavior of the growth function that's possible. All right, so this is quite a striking thing, and it means that the complexity of plus minus 1 valued functions in this worst case, this minimax sort of setting, is really very, very simple to describe. Right? There aren't too many different sorts of behaviors of plus minus 1 valued function classes, and we'll see what I mean by that a little later on. But let's think about an example, a non-trivial example for linear threshold functions on RD. We saw that the growth function had this form, and I didn't explain where that comes from. We'll see something, I guess, a generalization of this sort of idea, of this sort of result later. So we will get an idea of where this comes from later on. But if we just take this for granted, the growth function for linear threshold functions on RD, evaluated at m, has this form. Well, we can think of this, if d here is at least as big as m minus 1, right, then this thing is 2 to the m minus 1. Right? We just get the full sum. M minus 1 choose 0 through m minus 1 choose m minus 1. That's 2 to the m minus 1 times 2 is 2 to the m. Okay, so the growth function is 2 to the m, provided that d is bigger than m minus 1. And then beyond that point, we have 2 to the m, and we lose some of the terms, the ones that go from d plus 1 up to m minus 1. Right? So we've got something that's strictly smaller than m minus 1 when m is bigger than d plus 1. Okay, so just rewriting, as I stated it then, rewriting this inequality as when m is smaller than d plus 1, the growth function is 2 to the m. When it's bigger, it's strictly smaller. So the growth function evaluated at m, I just said that, it shrinks below 2 to the m as soon as m gets bigger than d plus 1. Well, this tells us that the VC dimension is equal to d plus 1. And there was a typo on a previous slide that I should have pointed out. So here I'm actually considering linear threshold functions with a threshold. I should have put a plus theta in here, where theta is a real valued quantity. Okay, so this expression is for linear threshold functions with an additional offset parameter. Okay, so there are actually d plus 1 parameters rather than the d I've written here. So this is a mistake. Okay, and then the VC dimension here, that's d plus 1. Well, that's just like that's the number of parameters, right, in this case. Okay, so here's an illustration in R2, and you see the decision regions here the decision boundaries are lines in R2, lines with an arbitrary offset. They're not all passing through the origin, right? So we have 3 parameters, a weight associated with each component of the x and an offset. And this is an example illustrating that we can get 8 dichotomies of these dichotomies plus the all 0, all minus 1 and all plus 1. So we can get 10 dichotomies of 4 points in R2. We can't get, in particular, 16, right? Because we can't get, there's no way to get minus 1, plus 1, plus 1, for instance, right? So so d plus 1 here is 3. We can shatter a set of size 3. We can't shatter any set of size 4, right? Can't get all 2 to the 4 is 16 dichotomies. Another way of looking at that, and here I've written it the right way with the additional offset parameter theta, is we could directly look at how many points we can shatter by this class of linear threshold functions, and you know, I won't step through the proof, but it's easy to see that you can shatter you can shatter m points if and only if these vectors of x1 minus 1, x2 minus 1, and so on. This means the concatenation of the vector x1 with the last component is minus 1. These m vectors are linearly independent. All right? If they are linearly independent, then we can not just get the signs right, we can actually get these values to anything we want, right? Just by inverting this matrix. If so, you know, we can certainly shatter a set that's linearly independent, and you can show that if they're if we can shatter a set, then they're necessarily linearly independent. And of course, that means we can find a sequence of m equal to the dimension plus 1 that are linearly independent, right? And we can and we can't find a set that's any bigger. So m can't be any bigger than d plus 1 to allow us to shatter, and we can find a basis of that dimension of this form. All right, so this is a direct proof that we can shatter a set of size d plus 1 but no bigger. The VC dimension is equal to d plus 1 in this case. Okay, so so we've seen that if m is smaller than the VC dimension, by definition the growth function is 2 to the m, so it's exponential in m. When m is bigger than the VC dimension, we get a polynomial rate of growth of the growth function, and this is called Sauer's lemma. Okay, so or sometimes called the Sauer-Shellach lemma. So here, if the VC dimension is no bigger than d, the growth function at m is no more than this sum of m choose I, right? So it's the sum of m choose 0 up to m choose d. So let me say a little bit about why this is true. All right. So I guess in the original proof that we saw, you know, using this sort of a result, we're working backwards. The growth function looks like this. You know, we have an equality here for linear threshold functions, and you know, as a result, we know how big m has to be before we drop below 2 to the m. All right, that tells us the VC dimension. Sauer's lemma tells us that in general we can go the other way, right? That when we know the VC dimension is less than some quantity, that tells us that the growth function grows no more than polynomially in m with exponent the VC dimension. Okay, so why is it true? There are I know of I guess 3 quite distinct proofs of Sauer's lemma. I want to show you the prettiest. So this is the shifting proof. So I want to write out that table. You remember I showed you an example of this table for the case of linear threshold functions on the real line. Right? This is the table of values that the functions take on a particular sequence x1 through xm. right? This is restrictions of functions to that sequence. So down here we have distinct functions. Each row corresponds to a function from our class that gives a distinct sign sequence, right? F at x1 is -1, f at x2 is +1, and so on. Okay, so here in this example, there are just 5 distinct rows to the table. So the cardinality of this set of restrictions is 5. We're counting rows in the table. Okay, and the idea of Sauer's lemma, all we're doing is saying if the VC dimension is no more than D, then the number of rows in the table can't be too large. Okay, so we're working to see that the number of rows is not too big. And the idea is to change this table into a form that that doesn't increase the VC dimension, but it's easy to count the rows. Right? Doesn't increase the VC dimension, doesn't change the number of rows, but it's easy to count the rows that we end up with in the transform table. Okay, and the transformation is as follows. So we work column by column. For each column, right, we change every plus to a minus if that leaves a row that isn't already in the table. So we're shifting down from +1 to -1 everywhere that we can that doesn't eliminate a row from the table. It doesn't leave us with a row that's already in the table. Right? So for instance, if we start with the first column and take this plus, we can shift it down to a minus because we'd be left with minus, 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 plus, plus, and we don't have anything like that. We don't have any row like that in the table. Right? This one's close, but it ends in plus, minus. Okay, then we can take this one and shift it down to minus, plus, plus, minus, plus, because there's nothing like that in the table. All right, if this had been a plus, then we couldn't shift that one down because we would be left with a row that was identical. Okay, so let's just do that shifting down column by column, ensuring always that we only shift when we're left with a distinct row in the table. All right, so here's the transform table in that case. So we saw if we start at the first column, we can shift everything down. When we go to the second column, we're left with the first. Let's think about that one. When we go to the second column, we have to leave this as a plus. Right? Why is that? Well, in the first column, we shifted that to a minus, so we had minus, 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 plus, plus. When we get to the second column, we can't change that to minus, 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 plus, plus, because there's already that row in the table. Okay? So we end up with a table that looks like this. All right, so what can we say about this table? Well, one observation is that if we ever see a bunch of pluses in a row, what do we know? Right, if I see 2 pluses like this, I know that somewhere else in the table I can change one of those pluses to a minus and I have to have that row. Or I can change this plus to a minus and I have to have that row. Right? Or I can change both of them to a minus and I have to have that row. Okay, so we have this closed below property, right? That if we were to shift anything down from here, okay, we would get a row that's already in the table. Okay, so I didn't mention, you work through all the columns and you keep on going until you end up with a stable, with a fixed point of this transformation. Okay, no more shifting can be done, and this is the table that we end up with after that full process. And so, of course, that it may mean that you need to work through the columns more than once. Okay, so what can we say about this transform table? Well, first of all, the size of the table is unchanged. Just by design, we haven't allowed any rows to disappear because if shifting down would have led to a row that was already there, we didn't do it. So we've got the same number of rows. Secondly, the VC dimension can't increase. Okay, so whenever we've got a row, whenever we've got our transform table shattering some subset of x1 through xm, the original table must have shattered some subset, shattered the same subset. Okay, and you can see that by thinking about what happens if we're left with after shifting a particular column, right? If we're left with a shattered set, so here we can see x4 and x5 are shattered, right? We have minus, 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 plus, plus, minus, plus, plus. Okay? If after shifting this column we're left with a shattered set, then we must have started with a shattered set. And that's, you can see that by considering that, well, we have a plus plus here. We didn't shift it down to a minus. Okay? And so we must have the identical row below that in the table. All right? And so, we've got plus everything and minus everything. So we've got a shattered set before we shifted that row. Okay, so shifting, if we have a shattered set after we've shifted, we must have had one there before. Okay, so we might decrease the VC dimension, but we can't increase it above its original value, which was no more than D. All right. Okay, so and the other property I mentioned already, that we've got this closed below property. Once we've done all the shifting, every plus that's in the table, if we change it to a minus, we get another row of the table. Well, this is the property that makes counting really easy. Okay, we know we haven't increased the VC dimension of a new table. We've got the same number of rows, but now we can count the number of rows. Okay, because every row has no more than D1s. Why is that? The VC dimension is no more than D, so we can't shatter a set of size D. Suppose we had a row that had more than D1s in it. We've got everything below that row. All right, so those D1s, that set of ones, right, is a pointer to a shattered set, right? If I find two plus ones here, then that indicates that the corresponding x's, x4 and x5, form a shattered set because I've got everything below these two pluses. So I've got the 2 cube. Okay, so I can't possibly have a row with more than D1s because the VC dimension is no more than D. Okay, so how many rows can I have that have no more than D1s, right, when I've got everything below? Oh, well, just how many rows can I have that have no more than D1s? Well, it's just the sum up to D of M choose I, right? M choose 0 is the number of ways of choosing a row with 0 ones, with 1 1, with all the way up to D1s. That's the number. That's an upper bound on the number of rows, right? And D here is our upper bound on the VC dimension. Okay, so the number of rows, since the size of the table is unchanged, the number of rows in the original table is no bigger than this sum. Okay? Yeah?
Do you have an example where the VC dimension decreases when you shift?
Where the VC dimension, yeah, you can come up with an example. I mean, I couldn't construct one off the top of my head, but there are examples like that.
And
yeah.
you also you mentioned that you need to come back to the same column.
You can come up with examples like that too, where you have to go through the table more than once.
And how often do you have to go through it?
Well, it's easy to bound that number just by arguing that you have a finite cardinality of the set of functions. I mean, that's a big bound. I expect that's really loose, but I don't know a better bound on the number of times you need to go through this operation. Yeah.
Thanks.
All right. So this is Sauer's lemma as I stated it, that if the VC dimension is no more than D, then the growth function is no more than this sum. You can estimate this sum. You can show that it's no bigger than something like m to the D. Do a little better than that. It's like m over D to the D. As long as this inequality is true, provided that m is at least as big as D. Right? Okay, so this tells us that the growth function grows only polynomially fast in D. All right, so when m is smaller than D, all right, we're not violating the polynomial rate of growth. We get this exponential rate of growth up to that point. When m is bigger than D, the growth function is no more than em over d to the d. So it's polynomial with exponent d in m. So nothing else is possible, right? The growth function has these two regimes, and the VC dimension really tells us what's happening there. Okay, so let's look now at, so that's the VC dimension and the growth function. Let's look now at what implications these things have for risk bounds, and in particular in a minimax setting. So we'll see that we can use our Rademacher averages results from the last hour to give bounds on to give uniform convergence results in terms of the VC dimension. We'll do that by relating the Rademacher averages to the VC dimension. All right, so just to remind you, we saw last time that with high probability, the maximal deviation between expectation and sample average. So I've used the notation here L sub f to indicate the loss function. The loss incurred, it maps from an xy pair to the loss incurred by predicting f of x when the true outcome is y. Right, if we look at the expectation of that function, that's the risk. This is the empirical risk, the sample average of that loss. The maximum over the class of that deviation is bounded by the Rademacher averages of the class plus some little bit. Okay, this is for plus minus 1 valued functions and L being the discrete loss. Okay, and as we commented, this thing is always small compared to this. You know, if n is big and delta is not too tiny. Okay, so I gave a one-sided inequality, but I commented that you could get the same thing in a two-sided way, right? Where you say that the deviations between expectations and sample averages are small. Okay, just by combining this inequality with the same thing for negations over here, and we want to make this statement in the two cases with probability delta over 2 and use a union bound, right? So probability at least 1 minus delta. All we're doing is changing the delta here to delta over 2, and we can make the same statement in a two-sided way. So expectations are uniformly close to sample averages with high probability. Okay, now that's in terms of the Rademacher averages, but we can relate these Rademacher averages to the VC dimension of the class. And I want to tell you a little bit about how we do that. So the theorem is as follows. If the VC dimension is D, then the Rademacher average, the expectation of these Rademacher averages is no more than something like square root of D over n, and there's some other log factor here, and a spurious parenthesis. All right, so it turns out you can do a little better than this inequality. You can get rid of the log factor at the expense of a worse constant. But actually n has to be really big for that to be a better bound. So how do we arrive at this square root, something like square root D over n? The Rademacher averages, remember the definition, it's the expectation of the maximal inner product between the vector of f of xi's and this random plus minus 1, this random direction in the binary n cube. Okay, so if we write that as an expectation of a conditional expectation, where this means condition on x1 through xn. Okay, so if we look at, so what's this inner conditional expectation doing? It's just averaging out the Rademacher averages, the Rademacher random variables. Right? So let's think about this inner conditional expectation. If we fix an xi, what does that look like? Well, you can show that inner expectation is no more than square root 2 over n times square root of this log of the cardinality of restrictions of functions in f, that should be a calligraphic f, to the sequence x1 to xn. Okay? And then we take the expectation of that. That's where this appears. So, you know, there's this inequality between the conditional expectation given the x1 through xn, so averaging out the Rademacher random variables, the plus minus 1s, that's no more than something like square root of log cardinality of restrictions divided by n. Okay, and we can take the expectation inside the square root log. Okay, this is, you know, using convexity. And Jensen's inequality. And so we get a result that looks like this. Okay, Rademacher averages in terms of expectation of this thing, of the cardinality of these restrictions. Okay, so this is an expectation under the random choice of the x1 through xn. Right? Now, the growth function is the maximum cardinality for all sequences of size n. So no matter what distribution we have, the growth function will give us an upper bound on this thing. Okay? So we can replace this with the growth function and get a result in, this is just throwing Sauer's lemma in there, right? The cardinality here is no more than the growth function, which is en over d to the d, as long as n is sufficiently large, right? And then take the log of that, we get this quantity, d log en over d. All right, so that's how we arrive at this result. The only question mark is, why is the expectation of this supremum no bigger than square root of the log cardinality over n? All right? Well, this uses the Hoeffding kind of ideas again. Okay, so this inequality, I guess I had a slide with a question mark there. So why is this true? Well, this uses the Hoeffding kind of idea. So let's think, here's a result that implies that earlier result. If we have some subset of Rn, so a bunch of vectors of length n, and all of them have Euclidean norm no more than r, right? Then when we take the expectation of the supremum over all of these vectors of sigma I times ai, okay, so this is an inner product between a vector in A and this plus minus 1 guy, this plus minus 1 vector, okay, the expectation of that supremum is no more than the radius here, right, of all of our vectors in A, times the square root of twice the log cardinality of A. Okay, so in our case, when we apply it, the set of vectors A is just the functions f restricted to x1 through xn, right? It's f of x1 through f of xn, vectors of that form as f ranges over our class. Okay, so what's the, in our case, all right, the Euclidean norm of these things, these are all plus minus 1 vectors, right? So the Euclidean norm is the square root of n. All of them have the same norm. They actually lie on the ball of radius square root n. And the cardinality of A is the cardinality of the restrictions of functions in f to x1, xn. So this is precisely that result, right? We take a 1 over n times the Euclidean norm, which is square root of n. That gives us 1 over square root of n times the square root of the log of the cardinality of A, or our set of restrictions. Okay, so this is a result. This tells us about actually the Rademacher averages of a finite class, right? And the proof here, this is due to Pascal Massart. It's a nice observation that that you can get this kind of upper bound on Rademacher averages for a finite class using the ideas of Hoeffding's inequality. So what we're doing here is considering a supremum over A, right, of this sum. Okay, so let's take e to the s times the expectation of this thing. This is the thing we're interested in, right? The expectation of the maximum over our set of the sum of sigma I times ai, this inner product. Okay, well, let's take e to the s times that and then use convexity and Jensen's inequality to pull the expectation outside. Right, so this is no more than the expectation of e to the s times that supremum. And we can pull the supremum outside as well, right? That's e, the expectation of the maximum over our vectors of e to the s z sub a. Okay? Well, this now is the moment generating function for this random variable. Okay? So, with this neat trick of taking an exponential e to the s times the quantity we're interested in and using Jensen's inequality, we have again a moment generating function. right? Well, not quite, I guess. We've still got a supremum in there. We can use the fact that the supremum is of positive things, so it's no more than a sum of exponentials, right? So we're bounding this supremum with a sum. And this is not a bad approximation here, right? If the maximum is dominated by one element of our set, if the sum is dominated by one element. And so, of course, then we're in the situation of looking at the moment generating function for such a random variable. Okay, and we use Hoeffding's inequality to tell us that thing is no bigger than e to the s squared times the 2 norm squared over 2. All right, we saw this in the last hour. You know, I just quoted it there, and I'm not gonna prove it here either. All right, but then that's no more than cardinality over a of e to the s squared r squared over 2, because our Euclidean norms are always no bigger than r. Right, and then taking logs of both sides and well, minimizing over s and taking logs, we get this result. Right, that this thing in here is no bigger than r times the square root of 2 log a, cardinality of a. All right, so there's a neat, view of a neat trick to get us back to this situation of getting nice bounds on moment generating functions for random variables. Okay, so that's the machinery that lets us get this relationship between the Rademacher averages and the VC dimension. Okay, the expectation of the Rademacher averages is no more than something like the square root of VC dimension over n. So we could throw that into the results that we saw last time in terms of the uniform convergence results that I quoted just a moment ago. So if we've got a class that has VC dimension D, then whatever the probability distribution, with high probability, the maximal deviation between risk and empirical risk, between the expectation of the loss incurred by f and the sample average of that thing, okay, maximizing over all f in the class capital F, is no more than something like square root d over n, with a log factor, and some small term, right? This is like log 1 over delta over n. All right, and then using the same ideas as we saw at the end of the last lecture, that means that if we minimize the sample average, right, minimize the empirical risk, then the risk is not much bigger than is no more than this plus the minimal risk. Okay, this is the best in our class, and this is some sort of a complexity penalty, right? An additional term that depends on the VC dimension D. So we get something like square root of d over n. Okay, and going from uniform convergence to this thing is very much the same as we saw last time. And I guess I've been a bit more cavalier with constants here, right? Because I guess we give away a lot with constants when we go to the generality of the VC dimension. Okay, so we could say something about the behavior of the empirical risk minimizer over some class of functions that has a finite VC dimension. Right? Its performance, its risk is no more than the best we could hope for from that class, plus something of order of square root d over n. Okay, so I already mentioned you can remove this log n factor here. You don't need that, but you need a more refined argument to remove that. And I'm not going to go into that. The more refined argument involves looking at covering numbers. And some results due to Dick Dudley. Okay, so the actual method that we're concerned with, the learning algorithm here, is particularly simple, right? Given our class capital F, we're just minimizing empirical risk. Okay, this is not very complicated. It's a very general result, and there are lots of approximations we've made along the way, but it turns out that the rate that we get here is minimax optimal. Right? This square root 1 over n is the right rate in a minimax sense. So we'll have a look at that. So here's the, first of all, I guess you can get rid of the log factor and get a result that's the Rademacher averages are no more than some constant times the square root of the VC dimension over n. You can refine that even and say that this notation, expectation sub sigma, means the conditional expectation, right, where you're just integrating out sigma. So conditioning on x1 through xn, you could get a bound on the Rademacher averages, the conditional expectation of these things, in terms of the VC dimension of the restrictions of functions in f to x1 through xn. Okay, so we're saying something that's somehow we're incorporating information about the distribution here in this sort of result. So you could also do that, although it's not so easy to get meaningful estimates of these things. So now let's look at, when I said a moment ago that this is a minimax optimal rate. What do I mean by that? How do we set this up as a what's an appropriate minimax setting here? What are we talking about? So let's define the following notion of estimation error. We've got a learning algorithm or a method, a mapping that takes us from training data to functions, and we don't care what those functions are. All right, so in particular, f hat here, it just takes as input x1, y1 through xn, yn, and the function L, it's just some mapping to functions defined on x. Okay, it doesn't. I'm no longer restricted to choose f from some class. It could be anything. Right? Could choose any kind of function here. Then let's define the minimax estimation error in this, n delta kind of a way. We have a sample size n, we have this confidence parameter delta. Then this is the best we can do over functions L, over algorithms or methods, right, of the smallest error that we could hope for at a delta level. Okay, so what does that mean? That means, is this an epsilon for which we can get the risk of f hat, the function returned by this method, within epsilon of the best in the class capital F. Okay, so here the criterion involves a class capital F. I'm not restricted to choosing functions from F, right? For any method here, what's the best method, whether it chooses from F or not, in the sense of minimizing the deviation between risk and minimal risk over that class F, all right, with high probability. Okay, we don't want that deviation to exceed epsilon with probability more than delta. And this has got to be true over all probability distributions. Okay, so whatever problem we're faced with, we want to have the probability that we have a worse than epsilon gap between the best we could hope for using F and the thing that our L returns, the risk of that, F hat. We want that probability to be small. Okay, so for the sample error minimization algorithm, that shows that this minimum is no worse than some constant times the square root of the VC dimension over n, essentially. Right? Because in particular, if we choose L as the element of capital F that minimizes the sample average of the loss, minimizes the empirical risk on this data, then we get that this epsilon, the deviation between the risk and the best in the class, right, is of order something like VC dimension over n, or square root of VC dimension over n. Right? So that's for sample error minimization that gives us this upper bound, and it turns out that that's essentially optimal in the minimax sense. It's the right rate at any rate. So as long as here's a theorem, as long as the confidence parameter is not too large, it can be treated as a constant, then for any class that has VC dimension at least D, this estimation error is at least as big as something of order VC dimension over n, square root of VC dimension over n. Right? We get exactly the right thing. And I put a minimum here because you can come up with silly things when the sample size is small to make this inequality not true. Right? So this is essential, but it's not something to worry about if you're thinking just about the rate. Okay, so this shows that the sample error minimization algorithm gives us this upper bound on minimax estimation error, and that upper bound can't be beaten, right? So as long as the class you're comparing yourself to has VC dimension at least D, then this minimax estimation error has to be at least as big as square root of VC dimension over D. Square root of D over N. I should have a D there, I guess. Okay, and that's, remember we're working, we've got to perform uniformly well across all probability distributions. All right, and that's crucial in proving the converse result for the minimax rate. Right, when we work with, so the idea of the proof of this lower bound is based on the probabilistic method. We choose a probability distribution that makes life hard for our learning algorithm L. Okay, and we do that in a random way, so that if I were to propose a probability distribution, you could easily design an algorithm that would work well for that particular distribution. What we show is that if you choose the distribution randomly from some set, then under that random choice you'll do badly somewhere, right? And so there must exist a probability distribution that makes life hard for you. All right, and so in particular when we look at the worst case over probability distributions, then you'll be doing that badly. Okay, so the set of distributions, this is all classical, but it's quite a nice proof. The set of distributions concentrates X on a shattered set and then chooses the Y's with probability, as plus or minus 1, say plus 1 with probability a half plus a little bit, or probably a half minus a little bit. You choose that randomly, right, whether it's plus or minus 1 here, plus or minus epsilon over 2, and you can show in that case that for whatever learning algorithm you have, the expected value of the excess risk, okay, expectation is now under the random choice of this probability distribution. The expected value of this excess risk is large, right, larger than epsilon, right, and therefore there must be some probability distribution that causes this difference to be bigger than epsilon. Okay, so this is the probabilistic method. We're showing that under some distribution, the expectation of the deviation is big. That implies there exists a choice here for which the deviation is big. And in particular, for a given L, we're not able to construct a bad distribution, one that hurts it. Right? We're just asserting the existence of it through this probabilistic method. Okay, so why is the expectation of this deviation large? The intuition at least should be clear. I'm not going to go through any detail, but we've chosen the distribution on the x's to be concentrated on a shattered set. So functions in our class can compute all plus or minus 1 valued functions on that shattered set where our distribution lies. So somehow for most points in the set, depending on the particular distribution, we set things up so that for most points in the set, we need to come up with a function that can guess whether the conditional probability of y being 1 is greater than a half or less than a half. And if we don't get that right for most points in the set, then we'll fail. We'll be epsilon far from the optimal thing. And it turns out in estimating these probabilities, you can't do any better than, a sufficient statistic is just to count up the number of, the proportion of points that you saw that took a particular value and had sign 1. And then compare that to a half. And now we're in a very familiar regime. We're just looking at tails of the Bernoulli distribution. We can't have the error of this estimate decreasing any faster than 1 over square root of n. So our epsilon has to be of that order, right? And the D arises because the VC dimension arises because we're having to simultaneously estimate these things over essentially all of the shattered set. Okay, so that's why the minimax rate, right? So just to summarize, that's why the that's why we get this inequality, okay? That the minimax estimation error is at least as big as order of VC dimension over n, and the minimization of the sample-based error over the class F, minimization of the empirical risk, exhibits this upper bound of square root VC dimension over n. So these two are just a constant factor apart, right? We can see that this 1 over square root of n is the right rate in this case. The VC dimension is the crucial quantity. If it's infinite, then we can't reduce the estimation error to 0. If it's finite, we can, and we know things go down like 1 over square root of n. And the optimal thing to do is just this very simple-minded, minimize the empirical risk. Okay, so in this estimation, in this minimax estimation setting, where this captures the VC dimension is the right notion of complexity of the class. But it is a little strange, right? It's a setting that's easy to criticize because you're looking at the worst case over probability distribution. And if you think about the proof of this inequality, all right, where constructing for every sample size n, we're constructing a probability distribution that that exhibits this lower bound. All right, so and we're constructing it in a rather strange way. All the y's have conditional probability. That's, I didn't write it there, I wrote it here. That's really close to a half, right? It's within epsilon or epsilon over 2 of a half. So it's a really hard, if we're looking down at this epsilon level, we're doing uniformly badly across all the y's. So the optimal thing is very close, has risk that's very close to a half, which is terrible, right? So, we're exhibiting the minimax optimal, that this rate we get is the minimax optimal using a distribution for which, we've got a very hard problem to solve here. Okay, so, it's not such a natural distribution that exhibits this lower bound. Okay, we can look also at a restricted case. So here we can worry about the case where there is some function in our class that always does well. So this is we can define what I call the zero risk minimax estimation error. Right, the subscript 0 here means that there is some function in our class, capital F, for which y equals f of x almost surely. All right, so this is a very strong assumption about the probability distribution. There's some function that gets things right. The Bayes risk, the optimal risk is 0, and there's a function in our class that makes the right prediction all the time. We have a deterministic mapping from x to y. So this is kind of the classical pack setting, for people who've heard the history, where you know that there's some function that gets everything right, and you want to be approximately correct, so within epsilon of the right thing with high probability. So just to go over, so what we're looking for here in the zero risk minimax case is for the best method. Right, how close to 0 can we get our risk, right, for the f hat that's returned by our method L, where the supremum here, so with high probability, with probability 1 minus delta we get within epsilon. So the supremum here is over probability distributions that satisfy this assumption that some f does perfectly, right, has risk equal to 0. Okay, so that's an extreme assumption, but we could consider this case. It turns out here that you get a faster rate, that doing empirical risk minimization, in this case we know there's some function in the class that gets everything right. So empirical risk minimization means choose a function from the class that's correct on everything, right? F of xi equals yi. Then with high probability, any such function will have risk no more than order of d over n, ignoring this log factor. Okay, and so the minimax, this is just, again, the sample error minimization approach, but it shows that the minimax, the zero risk minimax estimation error is no more than of order d over n times the log factor. And there's a similar probabilistic method argument to show that to show a converse result that you can't do any better than of order d over n, no log factor here, and actually there's a gap there, right, between these two upper and lower bounds. But you see we're getting a different rate now. This is like log n over n or 1 over n versus 1 over square root of n. So we get a faster rate in the case where the optimal risk is 0. So just to summarize, the situation when we're dealing with a plus minus 1 valued function class and we look in this minimax setting, things are really rather simple. All right? There's not a lot of different kinds of behaviors that are possible. Right? So to give a big summary of everything that I've said earlier, it turns out that all of these statements are equivalent. Right? If you want your minimax risk to go to 0, okay, then it goes to 0 at precisely a 1 over square root of n rate. Right? That's equivalent to the zero risk minimax estimation error going to 0. Right? And if it goes to 0, it goes to 0 at precisely, well, the theta tilde here means ignoring log factors. So we don't know, right, precisely the rate, but something like a 1 over n rate. All right? And if you want these things to go to 0, then, right, you want the minimax estimation error to go to 0, you need to have finite VC dimension. And that's equivalent to the growth function being bounded by some polynomial. So the growth function grows like some polynomial in n, in the argument. Okay, so all these things are equivalent. So we have, only a very limited range of behaviors that are possible in the plus minus 1 case in a minimax setting. All right, if you go to regression, things become much more complicated. You can get all sorts of different rates. Define analogous things, and you get all sorts of different rates in that setting. It's not, it's really rather richer. But in the case of classification, we don't have things are really much simpler.
So this is saying that if you have more data, you can follow your empirical data, try to minimize it, try to satisfy your estimator, and the Radimaker will be bounded to make that to very small.
At the Rademacher averages? Yes.
So if you have more data, then you want to satisfy all your training data, and it will be bound. Your estimator will be bounded by the training bound.
Right. So one other thing I didn't write down here, I guess, was that these rates are exhibited by the approach that minimizes empirical risk over the class F, right? And for that particular approach, we know we obtain the upper bounds on these rates via the fact that we get this uniform convergence between risk and empirical risk, between sample averages and expectations. So we know, as the sample size grows, that those get closer and closer together. The maximal deviations over the class between expectations and sample averages get smaller.
So in summary, if you have more data, you want to have your function. So you want to have your function to satisfy all the data. Training data.
That's not implied by these results. but something like that is true, right? I mean, these results say that it suffices to have the proof of these upper bounds say that it suffices to have to minimize the empirical risk, right? So as to achieve this optimal rate, right? N is the sample size. Yeah. Yeah. Yeah.
I think I missed. Can you tell me again about the constancies on the bounds of epsilon?
Constant C.
Yeah, C 1, 2, 3.
Oh, where? In
on the bounds of epsilon on page 64.
64. Okay, yeah, I mean, I'm just not specifying these constants, right? You know, they arose, the C3 here, I'm not specifying because, you know, I didn't tell you about the proof that gets rid of the log factor, okay? When you introduce a log factor, there's something like a 2 here, and we saw the proof that gives that, right? And actually, you know, the log factor then is rather innocuous. Unless the sample size is very big, you get actually a smaller number here than you would for this result, because so the proof involving the proof that leads to the 1 over square root of n rate without the log factor it goes via covering numbers and Dudley's entropy integral result. So Dudley has this result relating the Rademacher averages to an integral of a certain, you know, the square root of the log of the of a covering number, you know, the size of a set of functions that approximates functions in your class within some accuracy. So, you know, there's this big machinery and quite an indirect path that leads you to that result, and the constant here is not very good. You know, it's some big number. And I didn't specify these two constants, you know, they just pop out of this lower bound argument. These are not crazy numbers. This one's, you know, of the order of maybe 10 or 20 or something. Right? And you know, I don't remember what C1 looks like. Okay. So as I've stated it here, yeah, C3 is quite a big number, but we saw, you know, if you're willing to get the ever so slightly wrong rate in the upper bound, then you can get some small number in there. Are there any other questions? Okay, so actually that's a good point to stop. Okay, so next time we'll look at how we can estimate the VC dimension, you know, which we've seen is the crucial quantity in the plus minus 1 valued case. We saw this example of linear threshold functions for which the VC dimension is precisely the number of free parameters, and there's a big family of function classes for which that sort of relationship is true, where the VC dimension is related to the number of free parameters, provided that we can compute functions from our class rather simply, right, without too much work. So there's this beautiful relationship between the amount of computation you need to perform to compute a function from your class and the number of parameters and the VC dimension. And we'll see a little bit of that next time, and we'll look at also at large margin classifiers where things are rather different. There you have something much closer to a regression problem, and you don't have, you know, the kinds of rates that we get here. You know, the situation is very simple because we're dealing with plus or minus 1 valued functions. If you go to real valued functions such as AdaBoost or SVM's used, then you're in a different regime, and you know, it's the kinds of behaviors that you get can vary. There's one more question? Oh, yeah.
Back to page 60.
60?
Yeah.
Yeah.
Could you explain again what is Minimax distribution average?
Yeah, so here we're saying if we have a sample size n and a confidence parameter delta, we'd like to find out the best that we can do, the smallest high confidence deviation that we can have between the risk of the estimate that we come up with, the function f hat that our algorithm returns, and the optimal risk over some function in our class capital F. Okay, so what does it mean? Working from the inside out, right? This is the risk of f hat, the function that L returns on the data x1, y1 through xn, yn. Okay, so this risk is a random variable. It depends on the data, right? We're comparing it to the best we could do if we were to restrict ourselves to the class F, the smallest risk in that class. And we're interested in guaranteeing that that deviation is not bigger than epsilon. Okay? So we look at the probability over the sample of size n that the deviation exceeds epsilon. We want that probability to be smaller than delta. So with high confidence, the risk of the function returned by our algorithm L is within epsilon of the optimum. We want that to be true uniformly over all probability distributions. So no matter what the distribution is, no matter what problem we're faced with, we like this high confidence small deviation between risk and optimal risk, right, to be no more than epsilon. And then we say, so this is our deviation that we want, and we want to find it, we want to have the best algorithm, right? So what's the value of this deviation for the best case, right? The method or learning algorithm L that gives us the best case epsilon. Yeah? Okay, so the key features here are where we're trying to guarantee. So we could have simplified this, I guess, by throwing away the confidence parameter and said we want, I don't know, something like the expectation of the deviation between these two to be small, right? So bound instead the expectation of the difference, expectation over the sample x1, y1 through xn, yn of the difference between the risk and the optimal risk. Okay, and you get very similar results then. The log 1 over delta, because it's an exponential tail, it integrates out and just changes a constant. So you get very similar results, if you wanted to formulate it in that kind of way. But a crucial property of this, the minimax nature, is it's minimizing over criteria, over methods L of the maximum over probability distributions. Okay, because we're looking at the worst case problem that we could have been faced with. And in that setting, when we look at that worst case setting, then this is the right rate. Square root of v summation over n, or 1 over square root of n is the right rate. Any other questions?
Yes. Is there any connection with the Lemma description index?
Right. So minimum description length has this. You're worrying about how many bits it takes to represent a function from your class. So here you could think about what's the best? I mean, there are many connections. I guess this is a short answer. If we go and look at what did I do? If we go and look at the growth function, the definition of the growth function, back here somewhere. Right, this is the maximum over all x1 through xn of the cardinality of the set of restrictions of f to sequences x1 through xn. Right. So on the data that we see, the log of this cardinality is like the number of yes/no questions you need to answer, right? To specify which one of those functions you have. It's the number of bits that you need to represent one of those guys. If you assume that you're kind of equally interested in all of them, right? Then the log of that cardinality is the number of bits that you need, and that's precisely what appears in this upper bound, right? So if you look at, it's the log of this growth function that we get. I probably didn't write it out. I skipped one step in deriving that, but right, it's the log of this cardinality that arises. Okay, and then when you get an upper bound on that in terms of the VC dimension, right? You know, what you're doing is you're saying that the VC dimension is like the exponent in the rate of growth of the log of that, the exponent in the rate of growth of that cardinality. So the log of the rate of growth, which is like VC dimension times the log of something, is like the constant multiplying the number of bits that you need. Yeah. I mean, you could also relate these things to Rademacher averages. You can relate; they're closely related to covering numbers, where you're approximating functions in your class in some appropriate way, right? And you're looking at the cardinality of a set of approximating functions. You know, again, the log of that cardinality is the number of bits you need to describe an element, and you know, this is very closely related to the Rademacher averages. You can get an inequality involving the log covering numbers, you know, relating that to the Rademacher averages, for instance.
Okay. If the VC dimension equal to infinity, then this bound just meaning.
That's right. That's right. And the lower bound shows you that you can't hope to do well in that case, right? If the equivalence between this and these other statements means if the VC dimension is infinite, then in the minimax setting, you're in trouble. Right? Now, this is not, if we think about what's happening with support vector machines or AdaBoost, they're working with real value functions. If you think of thresholding, you know, the voting, the committee that AdaBoost uses, right? That's something that, you know, without a constraint on the number of functions you introduce, has infinite VC dimension. For typical reproducing kernel Hilbert spaces that we work with, like, you know, with the Gaussian kernel, for instance, right? If you threshold the functions that it produces, you've got infinite VC dimension. You know, we're really concerned here only with plus minus one valued functions, and that's the wrong way to look at those real valued function classes when you're optimizing a smooth criterion, as AdaBoost does and as SVMs do. Right? I mean, we're in a different regime when we're not working directly with plus minus one valued functions. All right, I guess we should have lunch.